Thank you very much for the introduction, and it's a big pleasure to be here and to present the company. So we are a quantum computing provider. We are not quantum chemistry expert as the previous speaker. So I will bring you today some perspective on our side to see how we can make this field advancing and how we have to work on our side to propose solution which fits the purpose. So I thank this previous speaker also because they highlight the effort and the methods in classical computing to do all this great work. And they also highlight how these problems scales in exponential time in a classical computer. And that's why quantum computing there can bring a solution because can bring this scaling on the linear side. So first of all, some introduction on the company. So Quandela is a Paris-based, in France and Europe, a quantum computing company created in 2017, one of the first in Europe. We are now 100 people with offices worldwide and with also a team here in Korea to engage with the community. We work at first directly on the engineering of quantum technology. We want from the beginning to provide solutions to industry. So we invested a lot in building a factory for assembling and testing quantum computers, and also to build a pre-industrial manufacturing line to build our photonic semiconductor devices, scaling the production, the qubits size, the number, and the performance. And with this, we managed to deploy already 2 quantum computing systems into 2 private data centers in Canada and France, and already put on the cloud 2 quantum processing units in a cloud which is open to all. The technology that we deploy is a mix in between the power and the connectivity and the speed of photons and the ability to create at high speed entanglement with atoms and spin. So we use semiconductor nanostructure, semiconductor quantum dots in this kind of devices, which are used to generate at high speed, at high rate, and in the deterministic way, high purity entangled photons in cluster states. And that's what we use to manipulate as qubits, and we manipulate them with standard photonic industry components like optical fiber and integrated photonic circuits. In the field of quantum chemistry, though, we see 2 different approaches coming. The one that exploit current systems, noisy quantum computers, and the one that start to look at error-corrected quantum computers. Clearly, we don't have error-corrected quantum computers today, so the approach today is to start with a classical simulation of the problem that you want to solve and an architecture for a certain platform, for a certain type of qubits, fidelity and connectivity, so on and so forth. So we try to estimate from the classical simulation the number of resources we will need in these upcoming error-corrected quantum computers. And the resources are metrics in terms of number of qubits, number of gates, operation, required coherence time, and even time. So companies started to look at that, as Boehringer Ingelheim in Switzerland, with Google in this paper, to try to extract exactly how this algorithm will perform on the future error-corrected, fault-tolerant quantum computing Google machine. And that's very important for the user perspective because they have constraints in timing, for example. So if a certain model of an architecture takes too much time for this algorithm, then they know that they may have to change platform or they may have to optimize the algorithm. So this is the first approach. Another approach is to do actual quantum computation on noisy system starting on small size problem. And that's an example of Moderna working with the team in IBM. In this example on mRNA, working on a certain number of qubits from 10, 80, 100, and therefore starting to optimize some current problems. So on the left, we can imagine we can use quantum computers today to optimize the accuracy of current models or increase the speed. On the right, we can do that, but we can also imagine to solve problems that we don't know yet how to solve. So clearly, at Quandela, we work on both. We start, of course, on the left with a noisy machine we have, and we're starting to prepare this simulation and this resource estimation service to company based on the current error-corrected architecture that we publish early on this year. On the left side, we have seen before, we can start to deploy quantum computing for molecular dynamics via a hybrid approach. This is called variational quantum angle solver. And this consists in solving the minimum energy of a certain Hamiltonian. We have to split it in parts and decompose the system. So we can run short, shallow quantum circuits in sequence, and we have, though, to run it many times. So the speed of the platform is crucial to deploy this kind of algorithms. Then, as you can see here, this is the kind of circuit we have to run. So we have to apply rotation to qubits, we have to apply logical gates. But the tricky part is that we have to define the so-called ansatz. We have to define a starting point to input to this system. And there are no models that can scale and that can prove a certain ansatz can provide a certain quantum advantage. So for each platform and for each problem, we have to work and define these ansatz. So it's a heuristic approach. It can work, it has been shown, but it requires a lot of knowledge and make the platform, the quantum computing platform, adapt to the system and to this kind of algorithms. So we started testing this approach on the toy model 2 years ago. We took the simple thing we could do, which is a hydrogen molecule with 2 hydrogen atoms, and tried to define and run it on our quantum computing system. So we started decomposing the system, preparing ansatz, of course, setting up the rotation for the qubits, and parameterize the system in terms of the position of the atom. Then you can see here, this is the current circuit we use. So we parameterize on the circuit certain rotation, a C0 gate, and other rotation. And what we do then, in a hybrid approach, we run this quantum calculation in parallel with the classical machine learning approach, where we can optimize the values, we optimize the loss function, and we set back optimize parameters. And we start to run this back and forth. And we run this several times because we need high accuracy, so we need high speed. And we run this for each of the points to reconstruct this curve that we all know. So this is our current data for each point. And what is important here is that we could run each point very quickly, compute it very quickly, and therefore run many of those to have the highest precision possible. And that's what we did for this example in the quantum processing unit Ascella, 6 qubit. And then we also ran it recently on this kind of molecule. And of course, now we are looking at more complex structure in the approach that was mentioned before, just splitting up and breaking up the molecule in different fragments, and work also with the expert in quantum chemistry to optimize this step, which is very crucial in order to make this platform more efficient. So now I want to tell you a bit more about the platform. How can this scale? How can this be helpful for this kind of problems? So this is the system which is available on the cloud since the end of 2022. It was the first single photon-based quantum processing unit available. And as I mentioned before, is based on a photonic qubit device, this object here that shoots single photon at high rate, and these are then enter into the circuit. They are first routed into several paths and manipulated here. Then the photons are detected, the output distribution is computed, and this gives results to the final user connected to the cloud. What it means is in practice for a developer is that we are able to operate these circuits. It's an interferometer, what photon enters here and exits here. So they enter and they get entangled, and they are manipulated through these blue sets. These are active phase shifters, so we can control very, very accurately the rotation of each single qubit and apply logical gates. So now the system is running with single photons. This is the current platform we use. For the end of next year, we plan to upgrade the system, just interchanging this module with the source of directly entangled cluster states. So the input will not be single qubits, but will be already entangled qubits. So we can, with the same structure, with the same infrastructure, push up dramatically the computing power and the number of parameters that we can manipulate. And this is what we need for this kind of problem, where you can see we have a huge number of parameters. So the effort we have put is also to optimize this on the user perspective side. So the 2.0 platform that we released a couple of months ago also provides an upgraded quantum processing unit. It's called Altair. It has 10 qubits which are fully connected. And this permits to develop and run quantum operation per second on around 500. We also embedded error mitigation with two kinds of methods, machine learning based and a protocol that we call photorecycling, and I can tell you more if you're curious. And this will allow to push fidelities up, you can see here. Another important point on the user perspective is that now we allow external user, industry, academic, or other quantum chemistry developers to reserve the platform at will. And because of the high availability, the platform is running 24/7, so we can provide customer all around the globe to access it with no need to wait for the results to come back to them. And another important point, which is plus in photonic quantum computing system, is the speed. So we can run thousands to millions shots per second, so we can have a very high accuracy in a very short time. This is important because the user doesn't have to wait for a long time. It doesn't have to pay for 15 hours to get a result. So two important points on the user side. Another important part, and at Quandela we are very, very focused and committed to it, is the benchmarking. How we can be sure that the algorithm we run is the optimum and is the optimum way to scale. And to do so, we push a lot on the emulation side. So we run the system both on our hardware, quantum hardware, and on emulators. And we push by running the emulators on AWS HPC on 9,000 cores. This is a record for the system. And we do so also with another method, running it on GPUs, on the latest NVIDIA GPUs. And what is important is that we see the threshold on 32 photons, which means that the boundary to the advantage is not on the 100 photon level, but very close. So the platform running today on the cloud is 10 photon, 10 qubits. We push it to 12 for the end of the year and 24 next year. So we start to be closer to this limit, to the classical simulable limit. And from the user perspective, provides points that can project to the region of quantum advantage. Another important part, as we are a quantum computing provider and not an expert in quantum chemistry, we make sure that we can provide the most optimized algorithms at the highest level for user. So we have set up this quantum algorithm toolbox where you can see we can run certain VQE or CVAR VQE application primitives without the need to learn how to program each parameter of the platform. So on the expert quantum chemistry part, they can simply take this optimized primitive, parameterize it to the problem, and then start to develop their solution. And to make this helpful for the community, we see that it's important that all the chain works together, so the quantum provider can provide the most upper level and optimized solution for the expert in chemistry can then optimize their algorithms and provide then to the end user this final optimized value. So to conclude, my message today were we can develop, we should work and continue working hard for developing quantum chemistry solution on quantum computers, starting on noisy system and looking far to error-corrected one because that's where the bigger value will come. VQE is viable on photonic quantum computing and provides a lot of room for improvement. So it's on our provider side now the hard work to make this more powerful. And then we see the importance of providing industry-grade solution. The chain has to be seamless. Every actor has to provide what's best for. So we provide the solution which are industry-grade, which are ready to be deployed by the expert in quantum chemistry for the final user. I want also to advertise that tomorrow, with the team in Quandela, we host a private event tomorrow afternoon where we'll present here our roadmap, so you can subscribe here. There will be hopefully space for everyone. And I thank you for your attention.
Thank you very much, Dr. Somaschi.